Hello everyone, welcome to this course on difference Galois theory. And application. I will mainly follow two references. The first one is a course by Singer. And if you want more details, you can find some in the book by Van der Poot. And Singer. So let me begin by an historical motivation. So I consider the Fibonacci sequences. So f of n plus 2 equals f of n plus 1 plus fn. And you certainly have seen at least one time that it satisfies the following functional equation. So of course, if I give you this functional equation and I ask you to prove it, it will not be very hard. You can just replace f of n plus 2 by the formula and then make an induction proof. But it leaves two questions. How to find such relation? And are there other relation or not? So the answer will be made with difference Galois theory. At the end, of course. So more generally, let us consider a vector that belongs to a ring and solution of a functional equation of this form. So I will be a matrix having coefficient in the field, and sigma is an automorphism. And with difference Galois theory, we attach to this equation a group that will be an algebraic group of J and of C that measure the algebraic relation between solutions. So let me begin by the first chapter. So, of Picard-Vector extension. And before talking about Picard-Vector extension, I need to make some reminder of difference algebra. So the Picard-Vector extension is basically the analogous of the splitting thing in this theory, meaning that it will be a set where the solution lives. And to do that, there is an extra structure, which is a structure of the automorphism sigma. So the difference algebra is just a classical commutative algebra, but with additional structure. So in this talk, all fields are of characteristic 0. All rings contains are unitary and therefore contains Q. So, definition. A difference ring or sigma, and most of the time I will just say R, is a ring together with an automorphism. Donc un automorphisme sigma from R to R. If R is a field, we say that it's a difference field. And of course, if R is an algebra, we say that it's a difference algebra, etc., etc. So difference just means that you add a structure. And there is a very important object that we attach. It's the subset of elements that are invariant under sigma. So it's called the constants. So exercise show that this is a ring, and if R is a field, then show that it's a field. So we'll talk about, most of the time it should be a field of constants. So most of the time we will say field of constants. Sorry. So let me make some example. So remind that we consider solution in R, which is a ring of equation of linear sigma equation over k. So here is the main example that we are going to consider. So no, sorry, so let me make this example just in 5 minutes. So before I need to make more definition on different algebra. Example will come in a few minutes. If R sigma and S tau are different string, difference homeomorphism is a ring homeomorphism that will called phi that will commute with zero automorphism. So you have to take in the right way. So phi come from R to S. So you can check that it's taken in the good way. And a very important object that will appear in this theory is the notion of ideal. So that R sigma be a different string. An ideal I is called a sigma ideal if, of course, it is an ideal, and sigma of E is contained in I. And a simple different string is a ring with only sigma ideals, so 0, and R itself. So it's the same definition as before. So let me enter into the main thing. So we are going to consider a linear difference system. So let K sigma be a difference field. Sorry. And let sigma of y equals a times y with a solving coefficient k different system. So we want to understand the algebraic relation inside R, the algebraic relation between solution. Inside R, a different string containing K. So this question may be seen as quite abstract. So let me make a few examples. So it will be the main example that we are going to consider. So the first one, it's the example we have seen just before. So it's the complex sequences. So sigma of un equals un plus 1. So I consider then over z because I want sigma to be an bijective. And k will be c, so the constant sequences. Okay, so let me consider another example. So it's a shift case. So R will be the meromorphic function over C. And K will be C of Z, and sigma of Fz is mapped to sigma F of Z plus H, where H is an automorphism, is a complex number. So in fact, we have to be a little more subtle at taking this, but at first approximation, let's take that. The Q case, so again, you may take the field this time of meromorphic function of C star. And Q is an element of C star, which is not of modulus 1. So here C is replaced by C star because 0 is fixed by the automorphism, so you need to withdraw it. So you may take R the field of Puiseux series. So it's the unions of a formal power series in an integral in a rational power of Z. K you will take rational function in a rational power of Z, and sigma f of Z maps f of Z to the P, where P is an integer bigger than 2. So here you have to take ramification because you want sigma to be inversible. And this example has its own interest because formal series, generating series of automatic sequences are naturally solution of Malloy equation of this kind, and it has been proved that if you are able to prove that a Malloy series is transcendental, then most of its value are transcendental, and it's very powerful because it used to be quite complicated to prove that a given real number is transcendental. And finally, the last example I want to consider, so it's the field of meromorphic function over C. K, it's meromorphic function over C that are lambda periodic, and lambda is the lattice of C, and so it's functions that have two periods, and sigma of f of z maps f of z to the h. So you want that this automorphism to be non-cyclic, so you want that h is a non-torsion point. So each of its example has been studied, so maybe the last one is less known, but now the case SUM are quite understood. So let me make a remark. So if you have an equation rather than a system, so since so the AI belongs to K, and since sigma is the automorphism, you can assume up to apply sigma minus 1. Sorry, that A0 and AN are not 0. And you can consider the the corresponding system. So for example, for Fibonacci, it will be the following system. And this matrix is a constant matrix. So we are in the case sec. So definition, a fundamental solution for our system is an invertible matrix having coefficient in a ring such that it's an invariant matrix, so I will call this matrix U, such that sigma U equals AU. So invertible is important, otherwise you could always take 0. So it's invertible. So an easy exercise is the following. So let U and V be two fundamental solutions. Show that U equals V times C, where C has constant coefficient. So it's just it's a straightforward computation, and we are going to reprove this result in few minutes. So if you want to be spoiled, you can just wait. So now it's time to enter in the heart of this chapter. So it's Picard-Vecchio extension. So in usual Galois theory, so you have an algebraic equation. So and in difference Galois theory, the basic object is a difference equation. And so there is the analogous of the splitting field, so which is a field that contains a solution. Here it will be a Picard-Vecchio extension. So it will be a set where you can solve your system. But unfortunately, as we will see, we will not find a field, but just a ring. So, definition. A Picard-Vecchio extension so from now on, I will just say PVX. For sigma of y stem AY, is a difference ring R sigma such that so it contains K and sigma extend from K to R. R is generated over K by X and the inverse product, the inverse of the determinant of X. So R is the fundamental solution. So note that once you have this relation, you have since sigma is a ring automorphism, you have that sigma of determinant of X equals of determinant of A times determinant of X. So you are able to define the image of every element. And finally, R is a simple difference ring. And this last assumption is totally crucial. Without it, you don't have uniqueness. So, in certain sense, you want to understand what are the algebraic relations between the solution. And the fact that R is a simple ring means that you form every solution. So, first of all, there exists a Picard-Vecchio extension, and if I additionally assume that the ring of constants of R is in fact a field of constants, which is the same as K, is algebraically closed. So then we have a uniqueness. Sorry for so if K is algebraically closed, so we have uniqueness. So let me prove this fact. So the proof of the existence. Excuse me. So in which chance we have uniqueness? So it means that if R1 and R2 are Picard-Vecchio extension, then there exists phi from R1 to R2 ring homeomorphism. So let me make a proof of this fact. So I consider an indeterminate matrices. So I consider outside that I caution by so I consider R1 type. So that I equipped with a different string structure with following rules. So R1 tile is now a different string. So it's good for the two first conditions, but I need a simple different string. So to do this, I will take a maximal sigma ideals. And then I will take the quotient. So R tilde is a simple different string. And is therefore a Picard-Vecchio extension. And the fundamental solution is just is the image of X in the quotient. So to prove the so this prove the existence. Now let me prove the uniqueness. To do this, let me admit the following lemma. So you can find proof of it in the book of Van der Poot and Singer. But if I prove every result, I will not be able to go very far away in this course. So that R be a simple K algebra that is a different string, a simple different string. So it's exactly the same assumption as the one required by the Picard extension. Then the field of constants of K is an algebraic extension of the field of constants of K. So now I am able to prove the uniqueness. I consider the tensor product of R1 and R2 over K. So it is a different string, finitely generated. But it is not a simple different string. So to force it to be a simple different string, I consider a maximal ideal, sigma ideal, sorry. So I call this field R tilde. So let U tilde and V tilde be image of the fundamental solution of R1 and R2 inside R tilde. So remind that R1 and R2 are Picard extension, therefore they are generated by fundamental matrices. So particular, we have sigma of U tilde equals A times U tilde, sigma of V tilde equals A times V tilde, and let's see having coefficient in gel or something, and we'll see what is the something. Such that U tilde equals V tilde times C. So I will apply sigma in both sides. So I use the fact that it's a ring morphism. And so, sorry, sigma of C. So I may, so this matrix, so I may simplify by A times V tilde, and it implies that C equals sigma of C. So by the lemma, we have R tilde. So the constants is the same as the constants of K. So it implies that C has coefficient in the sigma constant. So remind that I have assumed that K sigma is algebraically closed. Then the image of R1 and R2 inside R tilde are equal. So it shows that they are the same. So let me make two remarks. The first one is that when K sigma is algebraically closed, then the field of constants of R is the same as the field of constants of K. And the second one, that the solution of the exercise that I given you a few minutes before, that if U and V are fundamental solution inside R, then U minus U times V minus 1 is constant. So from now on, we are going to assume that K sigma is algebraically closed. Which is the case of every example that I've given you. So the fact that everything is defined over Q over C is due to the fact that we want field to be of characteristic 0 and algebraically closed. So it's two big constraints. So you can replace C by Q bar, but you cannot take anything you want. So let me make a basic example. So take the framework of the sequences. So here A is just the opposite of the identity matrix. And so it's quite natural to take so this field, so this string, so sigma of x equals minus x, so you want to have a solution, and you want to be a maximal ideal. So I take I. So sorry, it's not y square, it's x square. So we want to show that E is a maximal sigma ideal. So the only potential non-trivial ideal containing I are x minus 1 and x plus 1. So but if I consider sigma of x minus 1, so I use the fact that sigma of x is minus x, is equals to minus x minus 1, is equals to minus x plus I. So it's belong to x plus 1. And oppositely, if I take sigma of x plus 1, so if sigma of x with sigma of 1. So it's minus x plus 1. So it belongs to x plus 1. So it means that if you apply sigma to the first ideal, you arrive in the second. And if you apply the second, you enter into the first one. So there are not sigma ideal. So it implies that E is the maximal sigma ideal. So let's note that E is not a maximal ideal. The maximal sigma ideal. And this is the point where you find a very interesting phenomenon. Because since your ideal is product of two prime ideal, you find something that is not a field, not an integral domain. So we have R, which is the direct sum of R1 and R2 with R1, so it's the quotient by x plus 1, and R2, it's the quotient by x minus 1. And so you have sigma of R1 equals R2 and sigma of R2 equals R1. So we would like to make things less abstract. So you can solve your equation. So for instance, with the certain sequence with minus 1 and plus 1. So we have R, which is isomorphic to this concrete ring. And in fact, we can see that the inverse is itself. So in fact, it's just C of U. So you don't have to add the inverse. And if I take 1 plus U, so I find the sequence with 2, 0, 2, etc. And on the opposite, I find 0, 2, 0, etc. And so 1 plus U times 1 minus U equals 0. And note that we find the equation of the differential ideal. So why we consider this ideal is square plus 1? It's just that the square of your solution will be identity. So in general, you don't have a structure of field and for integral domain, and we will see that in a few minutes. So let me continue with further property of the Picard-Vessier extension. So the first one is the following. So we want to make the thing very concrete. So so I consider as before a difference equation and the equation k. So let R be a difference k algebra, and assume that k is an integral domain whose field of fraction satisfy that you did not add any constants. So it's the case in the KQ manner and sequence, but not in the elliptic case, neither in the shift case, because you may have add some constants. For instance, when you take homomorphic function over C, you may have add H homomorphic function, H periodic function that will be constant. So assume that A1 is a non-zero solution of sigma y equals A1, then there exists outside a Picard-Vecchio extension with y1 until yn is the first column of the fundamental solution. So how do we prove this? So we'll construct a Picard-Vecchio extension over the big field k. So of course, is A has coefficient in little k, it has coefficient in big K. So let X such that sigma of X equals AX with first column, so the vector solution, and I take, so it's not readable, I take the quotient, where it's maximal sigma algebraic. And so this I call it at over big K. So outside over big K is a Picard-Vecchio extension over big K with the good properties. So the first column is your vector y1 until yn. And the question is, and so now, so let U be the fundamental solution. Now consider, so we want a pk extension over big little k. So I consider since if you take the thing over big K, since it's simple, then the same hold. Otherwise, you will find non-trivial sigma ideal for the little ring. So is convenient. Pk extension. And this completes the proof. So okay, so now the last things that we are going to see is the fact that the pk extension is not always integral domain, but we can do a lot of, we can say a lot of things on it. So I consider sigma of y equal ay, where a belongs to gln over k. Then there exists an integer t such that any pk ratio extension is of the form, so it's the direct sum of R1 until RT, such that so the Ri are integral domain. So in general, the pk extension is a direct sum of integral domain. Sigma R equals y plus 1 modulo t, so it means that sigma of RT is R1. And Ri equals to EI times R with U1, UT that belongs to R, and UE, UG equals of 0 if E different to G, and UR if not. So it's an idempotent element. And Ri, so remember that it's integral domain. So if you consider the second property, it means that the sigma of C of I is Ri. So it's sigma T different string. That is a pk ratio extension for for the following system. So it's just the system, so sigma power t minus 1 of a, and you multiply to a, so it's just the system, so the initial system, but where you apply sigma t times. Okay, so until the end of this chapter, I will try to prove this result. So so let me begin by a lemma. Let R be a commutating if there exists is and belongs to R of X infinitely generated, then there exists I prime that belongs to I infinitely generated. So so let E be non-finitely generated, so E I non-finitely generated, and so let Fi so sequences of polynomial such that Fi is of minimal degree in E quotient by F1 until F I minus 1, and F1 of minimal degree in I. Okay, so I call Ni the degree, and Ai the leading term. So of course, by construction, they are in ascending order, and so I claim that A1 is infinitely generated. So which will be the end of the proof. So if not, let S such that A1 until AS equals to A1 until AS plus 1. Then, so by construction, AS plus 1 may be written in the following way. So E goes from 1 to S, and the BI belongs to R. Okay? And now, let me consider the following polynomial. So J f of S plus 1. And so I will construct a polynomial of less degree. So BI x to the n s plus 1 minus ni with degree of g. So by construction, degree of g is strictly lower, sorry, not strictly lower than degree of f plus 1. Sorry, let me write it properly. So with degree of g strictly less than degree of f plus 1, and j that is not generated that belongs to A minus f1 fs. And so we found a contradiction. So here it's a plus 1. And so we found a contradiction, and this completes the proof. So it led us to the following theorem. So Hilbert by this theorem. That says that any ideals of a multivariate polynomial is finitely generated. So let me make the proof by induction on n. So n equals 1. It's the lemma. Since K is a field, ideals of K are 0 and K itself, which are finitely generated. So, and if you want to go from n to n plus 1, so you just consider the lemma with K with R equal K of x1 to xn. So it's a commutative ring. By assumption, if you have a finite, an infinitely generated ideal, inside that you have an infinitely generated ideal inside that, but well, you just withdraw the x variable. And so you just apply the lemma n times. So there is a more simple way to see the things. So more generally, so it's just lemma applied m times with successively r, that is k of x1 to xk, k goes from 1 to n. So I let you as an exercise to finish to write the proof. And so if you have an infinitely generated, so you add them. So let me continue with lemma on ideal of a multivariate polynomial. A maximal sigma ideals is of the form so it's the intersection from 1 to n of pi, where pi are prime. So note that if you want a maximal ideal, you have n equals 1, because otherwise you would find a bigger ideal. But here, the automorphism sigma may permute the pi, as in the example. So proof. Consider the finitely generated ideal I, and the fact that k of k1 until kn is a factorial ring implies that you can write the pi as a decomposition into a product of prime factor and we may assume that no q algae in common. So this implies that you may prove that it's just the intersection of the qi energy, and but note that you have the following property, that sigma of q is inside the polynomial q square, so that so this implies that the NEG equals 1, since otherwise the intersection with power 1 will be sigma ideal containing I. So it's complete the proof. So now we are ready to prove to make the proof of the proposition. So the proposition of structure. So let R so I is again a maximal ideal, and it's an intersection of prime ideal. So if you have a subset invariant under sigma, then then the intersection of Pij is sigma ideals containing I. So necessarily R equals so sorry, I will call T to number of prime ideal. So R equals T. So it means that you can not take a subset of ideals that form a self-stable under phi or on sigma. So up to ordinate, we may assume that sigma of P1 equals P2, sigma of P2 equals P3, and sigma of Pt equals P1. So remind that you want to prove that R is a direct sum of integral domain and that are cyclically permuted by sigma. So the structure comes from the fact that the maximal sigma ideal is the intersection of T prime ideals. So the structure of the automorphism makes that but you find you don't find an integral domain. And so in particular you have that sigma of py equals py. So every py will make sigma t ideal. So now I claim that py is maximal sigma t ideal. How do I prove this? So otherwise, so let QE that contain it then the intersection it's so it's sigma ideals So you consider the intersection of sigma j de qi, so is sigma ideals that contains I, and remind that I is maximal. So it implies that it's just equals to I, and so on the other side, remind that A was the intersection of the pi. Sorry. So remind it means that there exists J such that you have the following inclusion. So for some J. So it means that G equals 0 and Qi equals Pi. So it proves the claim. So it means that the good candidate for the Ri are the following. So it's K of X 1 over the determinant that you quotient by Pi. So it's a sigma T pk ratio extension. The fact that you have a prime ideal makes that Ri is an integral domain. So it's a sigma T pk ratio extension for following system. So sigma T of y is sigma T minus 1 sigma of y, so it's sigma T minus 1 of ay, and I just repeat this procedure. So at the end, I find this matrix. So now it remains to prove that they are in direct sum, and we will almost finish. So I consider pi the canonical projection. With kernel I, of course. So if you consider E different to J, Pi plus Pj is sigma T ideal containing Pi and Pj. So it means that Pi plus Pj equals the entire ring. Since you have since I is maximal sigma T again. So the Chinese remainder theorem implies that R is the direct sum of the R ring. And if you take a generator of the ideal PI, then R the form EI times R, and the proof is complete. They are in direct sum, and so everything is proved.